Hi, how y'all doing? I am the only thing between you and lunch, so thank you for being patient. I guess we'll get started here. I want to talk to you today about functional programming. If you're not here to talk about functional programming, you're in the wrong room, so go out there. No. My name is Anjana, Vakil, and I am not a functional programming expert. I did not invent the lambda calculus. I am not even a long-time functional programmer. I am someone who's learning functional programming. I am a beginner, and I'd like to talk to you today a little bit about what I have learned about what functional programming even is, why it's kind of cool and definitely worth learning, and how we can write functional programs, particularly in JavaScript, since, of course, we all love or use JavaScript. So, really quick, the first question is, who is this person standing in front of you, talking to you, and hopefully not losing mic reception? My name is Anjana Vakil, as I said before. You can find me on Twitter at Anjana Vakil. I think I'm the only one. And I am an engineer at a small company called Uber Research, no affiliation with Uber, the cars. We work with data about scientific research funding, and so I create a domain-specific query language to interact with that data about research funding. I'm also an alum of the fantastic Outreachy program, which is an initiative to get more women and underrepresented folks involved in the world of open source by offering paid internships at really cool organizations that work on open source software like Mozilla. I'm still involved with Mozilla, even though I'm no longer an intern there. I am a volunteer and a Moz tech speaker. And I'm really happy to chat about any of those things in the breaks or at lunch. So if you're curious about, especially about Outreachy, if anyone out there is or knows any women looking for internships in open source, come talk to me. But for now, I want to tell you about one other organization that I am affiliated with, which is the Recurse Center. I'm an alum of, this is an amazing programming community and a programming retreat in New York City. It's a place where you can go for 3 months and work on becoming a better programmer, whatever that means to you. It's a completely self-directed thing where you just try to learn whatever is most interesting, most fun, most useful to you to get better at coding. And when I was there in the fall of 2015, I had been coding for a few years, but not professionally. I had been writing code that it did what I wanted it to do, but it wasn't necessarily pretty. It wasn't necessarily well organized, well laid out. It was hard to maintain. It was hard to go back and change later. It was not very reusable. And I felt like there must be better ways of doing this. So one of the things that I was asking folks about there is how can I write code that's really modular, really reusable, really easy to debug, easy to maintain? And a lot of people kept telling me, you have to check out this thing called functional programming. It's super cool. So I started asking myself, what is functional programming? And the first thing I learned is that it's a bunch of buzzwords. All of these words were flying at me all over the place, like higher order functions, and statelessness, and referential transparency, immutability, side effects, monoids. And there was this lambda character that kept showing up everywhere. And I was like, what is any of this stuff? How does this relate to me writing programs that are easier to read and easier to use? So I started trying to make sense of all these crazy buzzwords. And the next thing I found out was that functional programming is kind of a style of writing programs that's supported by some languages to a greater or lesser extent, and not supported by others. So some of the languages that support functional programming, pretty much anything that's got a lambda in its logo, you're good to go with the functional programming, like Haskell and Clojure. These are often called pure functional languages because they support only functional programming. Then there are languages like F# and Scala, which encourage functional programming and support it, but also allow you to kind of fall back to object-oriented programming when you need to, or when you want to. And then there's JavaScript. And JavaScript is great because we all know it already. or we're learning it, and it allows us to write code in lots of different styles: imperative, object-oriented, functional. So I don't have to go out and learn Haskell if I want to do functional programming. I can do it in JavaScript. That's cool. Okay, so what is this? What is the difference here? I've been talking about imperative programming, object-oriented. What is this that we're differentiating here? This is the idea that functional programming is a programming paradigm. So I started asking myself, what is a paradigm? And the understanding I got is that a paradigm is basically a worldview. It's kind of a way of looking at the world in terms of what the world is composed out of. And since we're programmers, our world is our program. What elements that's composed of and how those elements behave and interact. And in that sense, it also means it's kind of a mindset, a way of looking at the world of your program, a way of looking at your code. So some of the other paradigms that maybe we may or may not be familiar with, one is imperative programming, where the program, the world, is made up of commands. So your programs look like, do this, and then do that, and then do this other thing, and then do this fourth thing, and so on and so forth. So it's really a series of commands, and the order is important. We say first this, then that. So time is kind of an important concept in imperative programming, and with that comes the idea of values changing over time, which is what we call state. So then there's object-oriented programming, which says, okay, imperative programming is cool, but once we've got really complex programs, managing that state, the way those values are changing over time, gets kind of complicated. So what if we package them up into like little units, and we'll call them objects, and then they could just talk to each other by sending messages back and forth, which is essentially what we do when we're accessing methods on those objects. So one object's method kind of calls another object's method, which calls another thing, and each of them contains their own little state package. So that's one paradigm that's often contrasted with functional programming. So one thing we know about functional programming is it's not that. Okay, what else? Well, another thing that contrasts with imperative programming is declarative programming. So if imperative programming is programming with commands, then declarative programming is programming with sentences, like, this is what I want, computer. I don't care how you deliver it to me. I don't care what your implementation is. I just want what I want. So SQL is often used as kind of the emblematic declarative language where you just say, I want these things from this table. I don't care what you do, how you do those crazy joins. Just give it to me. Functional programming is sort of a sub-paradigm of declarative programming. It's more declarative, that it's on the declarative side of things compared to imperative programming, but none of these other paradigms, they haven't really answered my question, what is functional programming? It's not any of those, okay, cool, but what is it? What's the essence here? And I finally found out that actually it's not so crazy. It's not a bunch of crazy buzzwords, a bunch of academic terms. It's really, in essence, at its core, one very simple, extremely powerful, but very simple idea. And that I found most clear in an article by Mary Rose Cook, who was a facilitator at the Recurse Center when I was there. She wrote an article called An Introduction to Functional Programming, which for my money is definitely the single best introduction you could possibly read to it. It's short, it's sweet, it's great. Check it out. And in this article, she lays it out really clearly. Forget all the buzzwords. Functional programming comes down to one pretty simple idea. Use pure functions. Cool, what's a pure function? So, a pure function is a function that only depends on its inputs. It doesn't look at anything else from the outside world except the arguments that you pass to it. And it only returns its output. That's the only thing it does. It doesn't have any other effect on the world. It doesn't make any other changes than returning its return value. So let's look at an example of some impurity. This is a function I'll call greet that is not a pure function. How do we know it's not a pure function? Well, first of all, looking at greet here, it doesn't take any arguments. So this isn't necessarily always a red flag, but it's kind of a little warning sign that maybe we're not dealing with purity here. But if I start looking at the body, we see this variable name pops up. What is name? Well, name is something that I declared earlier. It's holding a string St. Petersburg. And my function greet is using that value name to create something, to do something. So already, aha, this is a sign this is impure, because it depends on something in the outside world that is not one of the values passed into it. Okay, but there's another thing very impure about this, which is we notice that there's not even a return keyword in this function. Huge red flag. Definitely not pure, because it's not returning anything. Instead, what it's doing is it's logging something to the console. This is doing something that is other than returning a value. It's what we call a side effect. It's changing the world in some way. In this case, it's changing what appears on your screen, other than returning a value. So this is a very impure function. And another signal for this impurity is I notice that if I call my function once, I get, my console says, hello, St. Petersburg. But then if I were to change name to be something else, like holy.js, if I call greet again, exactly the same way as I called it the first time, with the same arguments, which in this case is no arguments, but in any case, it's exactly the same call, and yet I get a different thing out. I get hello holy.js instead of hello St. Petersburg. This is another sign of an impure function. A pure function, when you call it with the same arguments, should always give you the same thing. So let's look at a pure version of this. So here I've got a function greet, which it needs to know something called name. So how do we get that information? Well, we pass it in as an argument. So here it's taking name as an input. And then instead of logging the string to the console, it's returning it. So now all it does is look at its inputs and use that to come up with its output, which it returns. That means if I call greet, I have to pass in the name that I'm expecting it to use. I could pass St. Petersburg, I could pass holy.js, but I can be sure that if I call it again with greet St. Petersburg, that I'll get the same thing as I did the first time. So this is really it. That's my whole talk. Bye. Just kidding, don't worry, you can't go to lunch yet. There's a little bit more that comes out of this, but this is really the core idea here. So a bit later in the talk, we'll look at some more patterns and tricks we can use to write functional programs, so how we can actually construct functional programs. But first, let's take a step back and look at why we might want to be doing this. Why is functional programming cool? So maybe some of you are already convinced that functional programming is nice. Any functional fans out in the audience already? A few hands. Okay, cool. But maybe some of you are like, I don't know, this seems like I got a thing about, I can't just log things to the console. That's super convenient. Why would I not want to do that? Let's see. So one thing is that pure functions are really predictable, because as we saw, the only thing they depend on is their input. And the only thing they do is return their output. So if you know what the function looks like and you know what's going into it, you can really easily predict what's coming out of it. And that becomes even more predictable when you start introducing in languages that introduce types, that you can make even stronger assertions about what's going to happen. But even so, even in JavaScript, where we're dealing with whatever types we want, who cares? We still have better predictability with pure functions than with those impure ones. Like with my first impure version of greet, if I change name, what do I get? I don't know. It depends on lots of other things. This means it's safer. It's harder to introduce bugs in your code. But it also means that it's easier to test your code and find bugs if and when they do occur. That's because when you're trying to test a pure function, all you need to do is pass in your test inputs and check if the output is what you expected. You don't need to set up a whole imaginary world with all of these states and mocked objects and everything, try and recreate the state of the world when you call this function. No, you just need to pass in whatever values you might expect and check that they give the right thing. And if they don't, if you're getting out the wrong value, then it's easy to track down where the bug is, because you know that if the inputs are right and the output is not what you expect, the problem must be within that function. It's not caused by some interaction with some other part of your program somewhere else. So this makes it easier to track down problems. So these are some good reasons to do functional programming. You might also hear some bad reasons to do functional programming. If anybody tries to tell you that functional programming is like smarter or harder or more hardcore than other paradigms, yeah, that's not really true, and that's not really a good reason to decide to use it for your code, to like look smart and look down your nose at everybody. No. Also, it's not the best of all the paradigms. It's just a paradigm among many. It has its strengths. It also has some weaknesses, which we won't spend a lot of time talking about today, but you can ask all those people that raise their hands. I'm sure they've run into a headache or two also with functional programming. So functional programming is great. Use it for the predictability, the testability, the easy debugging, but don't use it because it makes you feel cool or you think it's superior to other programming paradigms. Okay, that brings us to the question, maybe functional programming in general is cool, but we're JavaScripters. Why would we want to use functional programming in JavaScript specifically? So for me, when I started learning functional programming in JavaScript, one of my motivations was that I was trying to learn JavaScript, and JavaScript's object orientation, for me, is super tricky. I find it tough to work with. I find it tough to think about. Prototypes are very different from other object-oriented paradigms, and this is like usually what you expect, but sometimes definitely not what you expect, and that's always a headache. And I don't know if anybody else has run into bugs because, you know, this was bound to some other thing than what you thought. Anybody? Yeah, exactly. It happens, even to those of us who are perfect programmers and never make mistakes. So imagine a world where JavaScript didn't involve this. You didn't have to worry about which prototype methods you were using. You just eliminate all of that. It magically goes away if you use functional JavaScript. So that was cool, I thought. And the other thing that's great about doing functional programming in JavaScript is that you're not alone. There's a huge community out there of folks who already have built up libraries, tools, modules that make the life of a functional JavaScript programmer much easier. There's lots of folks out there willing to help you out, learning with you. So it's a good way to kind of start trying to wrap your head around functional programming, because you can do it within the existing community, and you don't have to go learn an entire new language, an entire new syntax. You don't have to go learn Haskell if you want to learn the first thing about functional programming. So, for this kind of long talk, I think maybe it's good if we take a breather for a moment. Maybe some of you out there who do functional programming in JavaScript, maybe you have other reasons that you like doing functional programming, or that you like doing functional programming in JavaScript. So perhaps we can take a couple minutes and y'all can share. Does anybody have anything they'd like to, any other motivations they'd like to add to our list of reasons why functional JavaScript is cool? Nobody? Okay, so those of you that do functional JavaScript, why? Cool, let's find out.
Well, because we're not writing just one program to work in just one project, and we want to write less. And we expect from our programs to do more than we just put in them. And functional programming, as I can see, it helps to make our programs more reusable, because we can simply take one part of the program and place it in the other program without even reassigning things in them.
Yeah, definitely. So the notion here is reusability. You can reuse functions that you've already built and kind of stack those together like Lego blocks, which is apparently the theme of this conference, is Legos. These functions become your Lego blocks, and we're going to look at a little bit later at how you can stack those blocks together and break them apart and stack them back together again. Really great point. Thank you. Anybody else?
Yes, maybe it affects on performance of your program, because of most of parts in program, it's less communicate with memory from your processor. Maybe in this way.
Interesting, interesting. So performance is definitely something that you have to take in mind when deciding whether or not to use functional programming. Interestingly, sometimes, and one of the reasons that I guess functional programming wasn't so popular in the industry until relatively recently, is that actually there are some issues with efficiency when you're using functional principles. And a little bit later, we're going to look at one example of that. And so I'm not sure how much you might want to use functional programming in order to make your code faster, but we have to also think about the fact that your code has to run fast, but you also have to be able to write it fast. You also have to be performant yourself as a developer, and so maybe functional programming with all of its great things like debuggability and modularity can help you be more performant, write your programs faster, and if you find efficient ways of doing it, you can also make sure that your programs are running as fast as possible. So yeah, great point. Performance is definitely something you want to take into account here. Okay, cool. So lunch is still not here yet, so let's press on so we can get closer to it. Let's do some functional programming. How do we do that? We write pure functions. Okay, how do I build a program out of pure functions? Well, we're going to look now at a few kind of principles you can live by as you're starting to write your first functional programs, kind of guiding lights, as it were. And the first one maybe is obvious, but I think it definitely bears mentioning, is that you should do everything with functions. Your program is going to be a function, which maybe is made up of other functions, which maybe are made up of other functions, and still other functions, and it's functions all the way down. The idea behind functional programming is that everything, the whole world, is functions that talk to each other. As we were saying, paradigms are about what is the world made up of? Functions. How do those components interact? By taking inputs and returning outputs. So here's an example of an imperative program that does not use functions to create its world. We've got a city, we've got a greeting. I'm basically telling the computer, computer, remember this string is city, remember this other string is greeting. Log this thing to the console, concatenating these strings together. So I log something to the console, I get something out, then maybe I want to change the greeting to, my Russian pronunciation is not great, but I'm going to say forget hi, remember, привет. And log that concatenation instead. So we get Привет, St. Petersburg. Ish. Y'all can give me Russian lessons after the break. Anyway, this is not functional. We're not defining any functions here. We are using the console.log function, but as we said, that's already kind of not very pure. So how could we do this in a more functional way? Well, we could turn our program, instead of a series of commands, into a function that I can call again and again. This time, we're going to take in a greeting and a name, and then return kind of a concatenation of all those with some punctuation in there. So now I can run my program by calling my function greet, passing in the inputs hi and St. Petersburg, and I get out the string, the output, hi St. Petersburg, and I can call the same function with different inputs and get out a different string. Привет, holy JS. So this is what you end up doing, is kind of thinking about everything in terms of functions. It's sort of like that, that saying, you know, when all you've got is a hammer, everything looks like a nail. Well, in functional programming, everything looks like and is a function. You just see functions everywhere. And we said that these should be pure functions. So one way we can ensure that we're writing pure functions is we can try to avoid side effects. What's a side effect? Well, we mentioned earlier that a side effect is something like console.log, which does something other than return an output value. So what we want to do is avoid that. We want to do nothing else in our functions besides compute and return our output. Here is a function with some side effects. I've got this object conf, it's got a name, it's got a date, and then I have a function rename conf. It takes in a new name, and the first thing it does is it assigns that new name to be the value of conf.name. Warning, side effect. This is our first example of a side effect because what it's doing is it's changing something in the world. It's changing that conf object that I had declared earlier that's outside of the function. But that's not a return value. And then it's got another side effect right after it. It's logging something to the console. We talked about that example earlier. And again, we see our huge red flag. It's not even returning anything. The only thing this function does are side effects. It doesn't have any main effect. It's just the side effects. So when I call this function, rename conf, I get my first side effect. I get the console log message that I renamed it. Cool. And then if I check what conf is, I see that it's changed from what I originally assigned it to. This is bad because maybe somebody else was depending on that conf being the way it was originally. Maybe they're not expecting this change. So here's how we could do that without side effects. Now I've got a new function, rename conf, which this time it takes in the old conference as one of its inputs, along with the new name. And what it does is instead of changing the value of the original conf, it returns a new object, which also has a name and a date, so it's the same structure as the original conf, but it's got the new name and the old date. So the thing that this function is doing, the only useful thing that it's doing, is returning a value, which I can then capture as new conf, and I can verify, yep, okay, new conf is what I expected, it's got the new name, but my original conf is still the same. And this is an example of a function without side effects. So this is a really, really major point for functional programming. It's programming without side effects. In fact, sometimes you hear functional programming defined as programming without side effects. Another thing that we saw in that last example was that in the side effecting function, we were changing something in place. That's called mutating data, changing it in place. So we want to avoid that. We want to avoid mutability and mutation in functional code. So the little rhymey mantra that I like to think of for this is that you shouldn't change something in place. Instead, you should replace it. And we saw that in the last example, where instead of changing conf, we created a new conf that we could use to replace the old version. So here's another example. Yesterday, we heard a great keynote from Douglas Crawford about numeral systems and numbers. And this was my kind of mental array of some various numeral systems. There was Roman numerals, I knew about those. I knew about Arabic numerals, we used those. Chinese numerals, I knew were sort of different. And then I attended that talk, and I thought, oh, actually, they're not Arabic numerals, they're Hindu Arabic numerals. They originated in India. Huh, cool, I didn't know that. So I had to replace something in my mental model. And I could do that in my JavaScript by just replacing the value at index 1 in my array of numeral systems. So I can take the value out of the original value at index 1, prepend Hindu to it, and then reassign that as the value at index 1. So that now my numeral systems array looks different than it did before. But it's the same array. I just changed something in place. This is dangerous because maybe one of my coworkers over there was working with my neural systems array because somehow we're mind melded or something, I don't know. And they were expecting that all of the values would be, they wouldn't contain hyphens, or they would be shorter than a certain length, or something like that. And now I've gone and messed everything up, and they've working with numericists, and it's different than what they thought, and there's bugs, and I get yelled at, and it's no fun, so let's not do it. Instead, what we could do is create a new version of my numeral systems array. So here what I'm doing is I am using the map, array.map, to create a new version that has the new values that I expect. So map is an interesting function. We're going to take a look at it a little bit later too. But it takes in a function, which is going to be applied to each thing in your array. And then it's each time it's applied, it's going to return something else, which goes into the new version of the array. So I just have to give it a function that checks the value, num, and sees if it's Arabic. And if it is Arabic, it doesn't return the original value, it tacks on Hindu and then returns that concatenated string. If it's anything that's not Arabic, it's just going to return the original value. So what I get now is a new array, which I can call new numeral systems, where I have Roman, Hindu, Arabic, and Chinese, but if I check my original array, it's still the same. So nobody's mad at me because I didn't break anything in any of their code. So So this is something that you'll get used to doing when you're doing functional programming, is instead of changing stuff in place, you end up creating new versions of it. However, there's kind of a problem with that. And we talked earlier a little bit about performance and efficiency, and that's where I'm kind of headed here. So let's think about it. When we have mutable data, if I have a regular old JavaScript array, we'll call it foo because that's a boring name, and we all like boring array names. It's got some numbers in it, 0, 1, 2, 3, all our old friends. But maybe I am now scared of 0 because 0 does weird things when you try to divide or multiply and stuff like that. So maybe I just don't want zeros around anymore and I want to change it to an 8. They're both round. It's cool. And this is fine in a world of mutability because I can just keep the same array. All the rest of the numbers are the same. I can change it back, I can change it to an 8, it's a 0, it's an 8, it's still my same foo, nothing else has changed. Cool. But again, we saw that that has a problem because somebody else was expecting that 0, and now they have an 8 and it's completely different and they're super mad at me. So what I could do is I could make this an immutable array, basically an array that once I've created it, it could never ever change. That's not really how JavaScript arrays work, but we can imagine an array that's just locked in place. And so that means that I can't just replace 0 by 8 in place. I'd have to create a whole new replacement array where I've got an 8, and then I've got all the rest of the values are the same. And this one I'll call 2, because it's like foo2. So this is cool because everybody that's using the old foo is still happy, nothing has changed for them, but it's not really cool because I had to allocate all that extra space for an entire new array. And I had to go through and copy each of those other numbers, the 1 and the 2 and the 3 and the 4, even though none of them changed. So this is taking up extra space, it's taking me a lot of time to do the copying, it's not very efficient. Now, of course, it doesn't matter when I've got a little array of 8 things, but if you imagine you've got like billions of arrays, or they're huge, or something like that, you can start to see where the efficiency would be a problem. So, there's a really cool thing called a persistent data structure, sometimes called an immutable data structure or a purely functional data structure. All of those things mean slightly different things, but they are often used interchangeably, and for our purposes, we'll just talk about them as persistent immutable data structures. And this is a way of efficiently handling immutable data. So the insight here is that instead of using a regular old array, what if I represent my array as a tree, where the leaves hold the values? So this is a special kind of tree called a trie. And those leaf nodes, maybe they have 1 value, maybe they have 2, like in this example, maybe they have 32. However many values they have, they are linked up together by an intermediate node, which then links to another intermediate node, and so on and so forth, until I've got one node at the top that unites all of my leaves into a tree that holds the same values as my original array. And this is my new foo. It's a tree now. What's cool about this is that if I want to change something, I don't have to change the whole structure. I just have to copy a really, really small subset of the data structure. So in this case, if I want to change the 0 to an 8, what I have to do is copy over that leaf node, but that's okay because it's only 2 things. It's much shorter than copying 8. And then I have to copy any of the other nodes pointing to the node that I changed, and then any of the nodes pointing to the node that point to the node that I changed, and so on and so forth, from the leaf that I want to change all the way up to the root of the tree. So I have to copy the path from the root, from the leaf to the root. And this still involves a little bit of extra work, a little bit of extra space, a little bit of extra time, but not nearly as much as before, because I don't have to copy a lot of the other stuff that didn't change. Most of this tree is shared between the 2 versions, between the original and the updated version. That's called structural sharing, and that's kind of the cool insight to these persistent immutable data structures. We can reuse as much of the old data structure as possible. Anyway, so this is a thing that I think is really cool because functional programming it's a great kind of high-level abstraction, but we need to make it performant, as we were talking about earlier. And so by using data structures that are designed to be both immutable and efficient, we can achieve that. Now, unfortunately, JavaScript doesn't have these built right in out of the box. Things like arrays and objects are not immutable, but there's lots of cool libraries out there that we can use to take advantage of these type of data structures in our JavaScript code. So here's a couple that I like. There are many more, but two of them are Mori and immutable.js. So Mori is a ClojureScript port. It's by David Nolan, one of the main folks behind ClojureScript. And it has a bit of a Clojure-y feel to it. It's got a functional API, meaning you do everything with these Mori.functions. And the names of them are a bit Clojure-y, and so it's a little bit, there might be some new words and some new terms that you'd have to get used to that aren't super JavaScript sounding, but it works great and it's really easy to use. Then there's also immutable.js. Immutable is by Lee Byron of Facebook. And it's, since it's by Facebook, it plays well with the React ecosystem and that whole thing. And it's JavaScript through and through. It's got a more JavaScript-y feel to it, including the fact that it actually uses a more kind of object-oriented feeling API. So you've got these methods on the immutable data structures. Like here, we've got f is a list, which is the immutable version of an array. In Mori, it's called vector. And so in immutable.js, you'd have a method on that list like push, which looks like maybe it's changing f, but it's not. It's just returning a new version, which I can capture. And they're both great. They have some trade-offs. Immutable.js is maybe a little bit smaller, perhaps better for client side. Mori is a bit bigger, but fast. So if you're using Node, maybe you'd want to try that out. And there's a lot of other alternatives as well. So I highly recommend you check these out if you're interested in keeping your code performant while sticking with immutability to make sure you don't change anything in place and mess stuff up for yourself and your coworkers and your future self, because that's bad. So, the next functional principle I want to talk about is iteration and not doing it, which for me was one of the hardest things to kind of wrap my head around when I was learning functional programming. In functional programming, you tend not to use iteration. Instead, you tend to use recursion to accomplish similar things. So here's some iteration that we're all probably comfortable with. I've got a sum function. It takes in an array of numbers, and then it uses a for loop to sum up all of those numbers one by one. Now, we notice here that I'm using the tried and true old school syntax here with the i's, because what we're actually doing is in the first round of the for loop, we're saying I is 0, and then we're doing something. And then in the second round, we're saying I is 1, and then we're doing something else, and then I is 2, and we're changing I all the time. So this is the type of changing of values and changing of variables that you tend not to see in functional programming, and instead, what you tend to see is a recursive function. So this is an example of a recursive sum function, definitely not the only way you could do it. But here, we're still taking in our array of numbers, and as in most, if not all, recursive functions, we've got a base case, which says, all right, in this one special case, if there's only one thing in numbers, then just return that thing. Don't do anything else. That's our base case. And then we have a recursive case, which is saying, if there's more than one thing in numbers, take the first thing and add it to the sum of all the rest of the things. So I see that I'm calling sum inside the definition of sum. This is a recursive function. It calls itself. And by doing that, I can go through all of the things in my array of numbers until I hit the last thing, so I've only got one thing left, and then I kind of pop all the way back up through all of the calls, and I've got my sum. And it works exactly the same way. It returns exactly the same thing that our iterative sum did. So thinking about recursion is something that becomes really important in functional programming, and it's something that definitely takes a while to wrap your head around if you're not used to writing recursive functions. But starting out with little building blocks like this can be a great way to do that. And another consequence of not using iterative loops is that you need some other tools to be able to go over everything in an array. And three of the tools that you'll end up using a lot are functions map, reduce, and filter. Now, these are really kind of fundamental tools in the functional programmer's toolbox, and some folks, including myself, when they first encounter them, find it a little hard to digest, to wrap their head around. For me, the best metaphor I have seen for understanding this, and I can't take credit for it, is the map-reduce sandwich. There's a link there. I did not make this. I did extend it a little bit to be the filter map-reduce sandwich. So the way these functions work is we start out with an array. In this case, let's say I have an array of ingredients, and I want a single thing. I want a delicious sandwich because I'm really hungry and I want to eat lunch. The first thing I could do to make sure that none of the foods that I don't like get into my sandwich is to pass it through a filter function. And a filter is just that. It lets some of the things through, but maybe not all. So filter takes in a function that returns a Boolean, a true or false. So maybe the filter function, the filter takes in a function that says true to everything and false to cucumbers and onions, because I don't like those. So it's going to apply a function that says, if it's a cucumber and onion, return false, otherwise return true. Apply that to each of the things. The cucumbers and onions stop there, and everything else gets through into a new array. So now I've got yummy ingredients. And in my nummy ingredients array, I have some whole vegetables. That's not really useful for making a sandwich, so I want them to be flat. So what I can do is I can pass that array to a map function, which takes in another function that will be applied to each thing in the array. In this case, maybe I have like a chop or slice function. Not slice like arrays, but slice like tomatoes. And so I'm going to pass in that function to map. It's going to apply it to each thing in the array, so I get a bunch of sliced ingredients. Now I have a bunch of chopped ingredients, and then I can combine them with a reduce function. Reduce is often also called fold, and it's a way of taking an array, and instead of returning a new array like filter and map does, it returns a single value that's kind of some kind of combination of all the things in our array. So in this case, maybe I pass in to reduce a function that's like stack or layer. And that combines all of my ingredients into a nice layered sandwich, which I can then eat. And now I'm really hungry and really looking forward to lunch. And I'm sorry for all of you, because we've still got a few more minutes left in the talk. All right, but this is filter and map and reduce. They're really, really useful, so definitely make sure we kind of internalize these functions. And I mentioned that those functions take in functions. They are functions that take functions. That means they're higher order functions. So a higher order function is a function that has as its inputs and or outputs other functions. Now, in order to create higher order functions, you need to have a language that supports functions being passed around just like regular strings or arrays. That's called first-class functions, functions that can be passed as values. And JavaScript has that, yes, and we're all super used to using that because I'm sure we all write a lot of callbacks and pass those into functions and things like that. So that's an example of a higher order function. Another higher order pattern that you come across is closures. So here I've got a higher order function called makeAdjectifier. What it does is it takes in an adjective and it returns a new function which takes in a noun and returns a string that applies that adjective to the noun. So for example, I could make an holify function by calling makeAdjectifier with the adjective holy. And then when I call that holify function on a noun, like JavaScript, I get holy JavaScript. And if I call it on cow, I get holy cow. Functional programming is cool. Dad jokes. Okay. Anyway, I've got here this holify function is kind of cool because it remembers something that's sort of outside of itself. It doesn't take adjective as an input, and yet it remembers what adjective was when it was created. It sort of remembers something about the environment when it was created. It's called a closure, and this is cool because it's not impure, and yet we're kind of being able to keep track of something from the outer environment. This is just one example of a higher order function. Make adjectifier here is higher order because it returns a function. Okay, the last point I want to make about how we can write functional programs, and for me, the thing that helps me when I'm trying to consider how am I going to write this program in a functional style, is to think about your program as data flowing through a bunch of successive functions, so that your program becomes kind of like a pipeline or like an assembly line, and the data that comes in, it gets successively transformed, and finally you get whatever result you want out. And what happens in the intermediary stages is that the output of one function becomes the input to the next function, whose output becomes the input to the next function, whose output becomes the input to the next, and so on and so forth. So here's an example. Let's say I have a function ender, which is higher order. It takes in an ending. It's kind of like adjectifier, except on the other side of the word. It takes in an ending, and then it returns a function that takes an input string and concatenates that, adds on the ending to the end of that string. So maybe I make a function called adore, which is an ender that adds rocks. And I make a function called announce, which is an ender that adds y'all. And I make a function called exclaim, which is an ender that adds exclamation point, because I'm really excited. I could combine those all into one function called hype up, which will take in whatever string I give it, and then will apply all of those functions one after another. And this is a little bit what we were talking about earlier when we were saying we can reuse things that we've written before, and we can build up bigger systems out of smaller building blocks. So here, I'm taking in whatever my X input is, I'm calling adore on it, then I'm taking the output of that, the return value of that, I'm calling announce on it, taking the return value of that, and calling exclaim on it. So that when I call hype up on something, like JS, I get JS rocks, y'all. And if I call it on FP, I get FP rocks, y'all. And I'm excited, just like all of you. Everybody's sleeping. Don't worry, lunch is coming in 3 short minutes. And this construction that I've got here, where I've got adore of X, announce of adore of X, exclaim of announce of adore of X, this is called function composition. And it's how we take those building blocks and we stack them up and we make a beautiful Lego castle. And a lot of the libraries that try to make functional programming as easy and as nice and as clean as possible will provide you with some kind of functions to do this type of composition. So this is an example from Ramda. Ramda is one of the many functional programming utility libraries out there. It gives you some functions like compose, for example. Compose takes in however many functions you want to pass to it and returns a single function that takes in its input and applies all of those functions one after another. So the first thing I've got here is this RTL hype function, which is the Ramda compose of adore, announce, and exclaim. But it works a little bit weird because Ramda's compose composes right to left. So it's gonna apply exclaim first, and then announce, and then adore, and I get this weird thing that's like FP, y'all rocks, which isn't exactly what I was trying to say. But luckily, Ramda also gives me the pipeline or pipe function, which is just function composition but left to right instead of right to left. And so that's how I can get first adore, and then announce, and then exclaim, FP rocks, y'all. So this is Ramda. It's one of the many libraries that you can use to give you these convenient functions to make your functional programming life easier so that you don't have to write all of these stacked parentheses calls. It's a lot cleaner and maybe easier to read it left to right in the order that you expect it in one little definition. So that's why you might want to depart from regular old vanilla JavaScript and start using some of these functional libraries or functional helpers to start writing functional code that looks as nice and clean and readable as possible. And Ramda's not the only one. We looked at Mori earlier. Mori, in addition to giving you the persistent data structures of Clojure script, also gives you some helpful utility functions, like for composition and pipelining. And then there are other libraries like underscore, Lodash. There's little NPM modules if you just want one function. There's like curry. There's lots of cool stuff out there. And if you start to use functional JavaScript and you start to feel, okay, I really like this. I would really like to live in a world where like it's purely functional and that's all I can do. Then there's tons of languages out there that are functional and compile to JavaScript. Like yesterday, Patrick gave a talk about ReasonML, or mentioned ReasonML. I mentioned Clojure script is an implementation of Clojure that compiles to JavaScript. There's Elm. There's lots of choices out there. Personally, I find it great to get started with JavaScript just to wrap my head around functional programming and then start learning the more purely functional languages. In any event, if nothing of what I've said up here today has made sense, or if some of it has made sense but you'd like to learn more, I have some links for you. I guess the slides will be posted to the conference site eventually. If not, I'll tweet them out. There's some really great articles you could read in the CodeWords publication from the Recurse Center, like the Introduction to Functional Programming that I mentioned earlier. There's also some other good articles in there you can find by my batchmate Sal Becker, and there's another good one by Patrick Dubroy. I'd also recommend checking out Jessica Kerr has some great talks about using functional principles in your object-oriented code, just bringing in like a little bit of functional programming. This talk that's linked here is a bit more focused on Java, so if anybody does Java, that's cool, but even so, the principles in general are the same. If you're curious about immutable data structures, a bunch of good talks on that by people like David Nolan and Lee Byron, the creators of Mori and Immutable.js. And I also highly recommend you check out a talk called The Miracle of Generators by Bodil Stock. It might not seem like it's about functional programming at the beginning, but stick with it. I think you'll find it interesting. So that's all I had. I'm Anjana Vakil. You can find me on Twitter. I want to give a big shout out and thank you to the folks at the Recurse Center, especially Mary Rose Cook, Sal Becker, and Khalid Ali. They are the ones who introduced me to functional programming and helped me wrap my head around these. So huge thanks to them. And big thank you to Holy.js for having me. I guess we have a few minutes for questions.
Hi.
Hi.
Thanks for your great and expressive speech. That was awesome.
Thanks for listening.
I try to learn about functional programming about 1 or more year, and I never seen information about which reason we have to split our code in blocks, modules. How to our pure small functions we organize in application. What can you say about this?
Sure. Well, so I guess this question touches on the issue of modularity, which is kind of more general than functional programming. Functional programming, I think, is one way of handling or picturing modules as functions. So like as we said earlier, you can take those functions and combine them together in different ways. You could, in my last example there, if I wanted to create a new function that instead of adding, I don't know, y'all, it adds you folks or you guys or everyone or some other gender neutral plural pronoun. I could reuse the adore and the exclaim functions as kind of like little modules. But then the question is, okay, what is a module? How, is a module like an entire program? Is it one tiny function that just adds an exclamation point? Like, what is it? And for that, I would really recommend, I saw a great talk on this just recently at JSConf EU. Ashley Williams gave a talk about modularity and kind of exploring this. She works at NPM, so I guess if anyone would know about modules, it would be her. Check out the video. I think it's on the JSConf YouTube channel.
Okay, thanks. And one more small question about non-pure functions. We must interact in real world, and where we must we split our code in pure functions and non-pure functions, or we can keep them together?
So great question. The question is, all right, I think if I may restate it, pure functions sound cool, but we live in the real world. We need to do things like print stuff to a console, like we just need to. We need to handle input and output and things like that. So how do we do that in a functional world? In general, the idea, and I think that this is something, so I didn't talk about it in my talk because for me this is something that is kind of the clincher. This is one of the downsides of functional programming, is that it's a little bit harder to see how that works. But what you can do is kind of isolate those side effects, isolate those impure functions into just maybe the outermost function of your program, something like that, and have everything else inside be pure. It's one way of doing it. There are also clever ways that functional programmers and functional languages have come up with dealing with this, sort of trapping inputs and outputs that are not pure in a pure construction. And this is where things like monads, the scary, scary word, come up. Douglas Crockford has a great talk about that, and trying to think about that for me was made most helpful by this talk at the end here by Bodil Stock about generators in JavaScript. And I'm not going to give any spoilers about that, but I'd highly recommend checking out that. And in general, trying to think about isolating the impure parts of your code in like a little safe space where you know where the impurity is, so that it doesn't come back to bite you in some other part of the program. Any other questions? Who?
Okay, thank you. I have a question about one of principle you said in your speech. You have said that we should prefer using recursions instead of loops. And you give one example with calculating sum. I just tasted this example, and array was numbers was 1000, and function with recursion works 2 times longer than loops.
Sorry, I didn't hear the last part. Could you repeat the last part? It was very badly, it was performing badly, I guess, with a large...
2 times longer, with 1000 numbers.
Yeah.
And what you say about this?
Well, what I say about that is another thing that we mentioned earlier. Performance and functional programming are definitely 2 things that we need to kind of trade off, because recursion, as you note, is not usually as easy to make efficient as iteration. The general idea behind that is that when you're doing a bunch of recursive calls to a function, you end up having to add on a bunch of new stack frames, one for each call to that function. So that's how you can end up overflowing the stack. If you have a really big array and you're calling that function a gajillion times, it goes up to the stars. One way, one technique for dealing with that is tail call optimization. So this is an optimization that allows you to rewrite certain recursive functions in a way that allows them to reuse the same stack frame over and over again. So time-wise, it'll still have to keep but you won't run out of space on it. You won't blow the stack. And sorry, did you want to cut me off?
Yes, I understand, but I think in this example it was not is dealing with stack, a call stack. It's a slice. It's a very expensive operation in this example.
Okay, sure. Yes. So this is another thing. I wouldn't normally write this function using using a regular JavaScript array and using the slice method. I would probably be using something like a Mori vector and using a tail or something like that, or immutable or whatever other library we want to talk about. So that is one thing, which is dealing with those individual operations. Once you've got lots of repetitions, which is what happens in this recursion, you end up kind of that adds up. So even a small, costly operation when you're dealing with recursion can become very inefficient. So absolutely, recursion is generally less efficient than iteration. The thing is that functional programming so recursion is kind of like perhaps arguably easier but different way to think about the code. And the problem is the connect between the way you, the human, are thinking about the code you write and the way the computer is executing the code you write. And so that's a problem where you want to be looking at what functions you're using, what operations you're doing. You want to just, same as anything, you want to make sure that if you're calling something a gajillion times, it better be fast. But just to go back to what I was saying earlier about tail call optimization, which is something that you've also been perhaps hearing a lot about in the JavaScript world more recently. This also wouldn't help with this function because this is not a tail recursive function. I don't know how much time we have and whether it makes sense to talk about what those are. I guess we can chat about it over lunch if anybody's interesting, but the way you would generally make this more efficient is A, by using more efficient operations or more efficient data structures so that you don't have to be copying them over and over again, and B, by rewriting the recursive function in a way that it can be optimized if your compiler, in this case, or if your engine makes that optimization, that sort of tail call optimization, and you write the function in a way that it can make use of that, then you get a much more efficient function that can run for as long as you need it to. So that's what I have to say about that. Recursion is not generally efficient. Iteration is efficient. That's why you see a lot of really performant code written in languages like C. Because when you lose the overhead of trying to make programs more human level and not so machine level, ones and zeros, there are costs.